Now in part 2, here we will discuss today the rate law expression and rate constant. What is rate law expression? Consider this a hypothetical equation where capital A, capital B, capital C and capital D, they are reactants. Small a, small b, small c and small d, they are their stoichiometric coefficient. So for this reaction, when the rate law is the mathematical expression which gives the actual dependence of the reaction rate on the concentration of reactant and is experimentally determined. Here this is the rate law expression, and in this rate law expression the value of x and y is determined experimentally. So we cannot predict rate law merely by looking at the balanced chemical equation, but it must be determined experimentally. Here this k, when we talk about this rate constant k, as we have already studied, the rate is directly proportional to the molar concentration of reactant, and the value raised to power molar concentration of A raised to power x and molar concentration of B raised to power y, the value of x and y is determined experimentally, and when we remove this proportionality sign, we write this constant, that is proportionality constant. This is the rate constant, and the A and B are the reactant, and x and y are their powers. These value of x and y may or may not be equal to their stoichiometric coefficient. So when we define this rate constant k, we can say the rate of the reaction when the concentration of each reactant is taken as unity. Here these are the reactant. When their concentration, molar concentration is taken as 1, then the rate of the reaction becomes equal to k, and this rate of reaction becomes equal to k, means rate constant. So we can define the reaction rate when the concentration of each reactant is taken as unity is known as rate constant. This rate constant depend upon the temperature. It is constant at a given temperature. The rate constant is not depending, means independent of the concentration of reactants. So these are the characteristics of rate constant. Now what is the order of the reaction? Just before we have discussed this equation where capital A and B are reactant, capital C and D are product, small a, small b, small c, small d are their stoichiometric coefficient. And when we write the mathematical expression for rate law, this is the expression for the rate law. Here rate of the reaction is equal to rate constant k, molar concentration of reactant A raised to power x, molar concentration of reactant B raised to power y. And as we have already studied that the value of x and y are determined experimentally. After determining these values experimentally, in this rate law expression, the order of reaction with respect to A is x. This is the value of order of reaction, and with respect to y, the order of reaction with respect to B, the order of reaction with respect to B is y. And if we want to know the overall order of the reaction, the order of reaction with respect to reactant A is x, with respect to reactant B is y, and total or overall order of the reaction is x plus y. So how can we define the term order of reaction? The sum of the powers to which concentration terms are raised in rate law expression. So this is rate law expression, this is the sum of the powers of the reactant. But they should be measured experimentally according to the rate law. So this is the definition here. The order of reaction with respect to reactant A is X, with respect to reactant B is Y, and overall order of the reaction is X plus Y. Remember that the value of X and Y are determined experimentally. Here the order of reaction can be 0, can be 1, 2, 3. It can be fractional or negative 2. There are different reactions where the order of the reaction can be in fraction or can be 0. For example, if we say decomposition of ammonia on platinum surface is a 0 order reaction. If we see the fractional order reaction, the decomposition of acetaldehyde into methane and carbon monoxide is a fractional order reaction. So here, if I want to write this equation, this is the decomposition of ammonia on platinum surface, N2 plus 3H2. Here the rate is equal to A rate constant. This is molar concentration of ammonia raised to power 0. Means the rate of decomposition of ammonia is not depending upon the concentration of the reactant ammonia. That is why it is a 0 order reaction. So it is a 0 order reaction. In the same case, if we want to see a fractional order reaction, this is acetaldehyde, and when it decomposes into methane and carbon monoxide, it is a fractional order reaction. Its order is 3/2. So the reaction order can be negative. Now you will search in what type of reactions the order of the reaction is negative. You have to note down the example of such reactions also. So depending upon the total order of the reaction can be 0 order, first order or second order. Here again we have considered a reaction where reactant A is converting into product, and the rate law. Here the order of reaction with respect to reactant A is n, small n, and from this order of reaction we can calculate the unit of rate constant by this expression. We know that rate is measured in concentration upon time. In place of concentration we can write mole per liter per time. Here the concentration of A, it is measured in mole per liter raised to power n, and this relation will come out from which we are able to calculate the unit of the rate constant. For example, this is a 0 order reaction. For 0 order reaction, we write the expression rate is equal to K. This is a reactant raised to power 0. And raised to power 0 means once the unit of rate of the reaction is mole per liter per time or mole per liter per second. Since raised to power 0 is equal to 1, so the same will be the unit of rate constant. So this is the unit of rate constant K for 0 order reaction. In the case of the first order reaction, this will be the expression rate is equal to K. Concentration of reactant means rate of the reaction is directly proportional to the concentration of the reactant. Here the unit of rate is mole per liter per second. This is the unit of the rate, And to calculate the unit of rate, this is mole per liter. Here molecularity of the reaction. Here this concept is generally valid for elementary reactions. Means the number of molecules which collide simultaneously to bring about the chemical reaction. In elementary reaction, this number of colliding molecules which collide simultaneously is known as molecularity of the reaction, and it is taken for elementary reactions. For example, here 1 mole of ammonium nitrite is decomposing to give 1 mole of N2 and 2 mole of water. Here 1 mole of ammonium nitrite is being used. Here it is an example of unimolecular reaction. In second example, it is 2 mole of HI are decomposed to give 1 mole of hydrogen and 1 mole of iodine. It is a bimolecular reaction. Its molecularity is 2. In the same case, 2 mole of nitric oxide react with oxygen to form 2 mole of NO2. Here it is a trimolecular reaction. So this is the concept of molecularity, but remember that molecularity is a theoretical concept while order is measured experimentally. Molecularity cannot be fractional, molecularity cannot be zero, but the order can be fractional as well as zero also. So the difference between order of reaction and molecularity of the reaction is also asked. As I told you that molecularity is meaningful for elementary reactions. It has no meaning for complex reactions. And what are elementary reactions? One step reactions are known as elementary reactions, while those reactions which are taking place in several steps, then they are known as complex reactions. And in those cases, the lowest step of the reaction determines the rate of the reaction. That is why it is known as rate determining step or RDS. The lowest step of the reaction is known as rate determining step, because it determines the rate of the reaction. This is the difference between order of reaction and molecularity. Here we have already discussed this difference. You can write in first point the definition of both the concept. Then molecularity can be zero, molecularity cannot be zero, order can be zero. Molecularity is a theoretical concept. It is determined experimentally. So if you will remember their definition, units, and the basic differences, you will be able to solve the questions asked in the exam. Here we have used the term order of the reaction. When we talk about the order of the reaction, order of reaction is determined experimentally, as we have already discussed. So the different methods used to determine the order of the reaction are: number 1, integrated rate law method, graphical method, initial rate method, half-life period method. These are the methods which are used to determine the order of the reaction experimentally. We will discuss first the integrated rate law method. These are integrated rate equations for zero order and first order of the reaction. For a zero order reaction, where we consider this reaction where reactant R is converting into product P, the differential rate equation will be minus dr upon dt is equal to K, molar concentration of reactant raised to power 0. Means for a zero order reaction, the rate is independent or not depending upon the concentration of the reactant. And you have already studied that any quantity raised to power 0 is equal to 1. So here we can also write this reaction like that, or this reaction like that. when we integrate the above equation, we find this relation. This is the concentration of reactant R after time t. This is the initial concentration of reactant R naught. K is the rate constant, T is the time. We can also write this reaction like this, and this reaction is equal to Y is equal to Mx plus C, and we can plot according to this reaction A. Here, when we plot concentration of reactant against time, reaction for zero order reaction, here we have plotted this concentration of reactant along y-axis, this time on x-axis, and the plot is a straight line with a negative slope. Here the slope is equal to minus k, and the intercept, this r naught is the intercept for this plot. So for a zero order reaction, this type of plot is obtained according to this reaction. When we plot, this is the molar concentration of reactant against time. This is the slope and this is the intercept of this plot. Here, sometimes when question can be asked that when the concentration of reactant is plotted against time for a zero order reaction, what will be its slope? Or if slope is given, he can ask about the order of the reaction or about the intercept of the plot. The same integrated rate equation can be derived for first order reaction. Here the same equation is there, reactant are converting into product. Then the differential rate equation becomes minus dr upon dt is equal to kr, where r is the concentration of reactant, k is rate constant. It is, and we can also write this equation like that: dr upon r is equal to minus k into dt. On integrating the above equation, we get this equation. This is natural log. Ln means natural log of the concentration of reactant minus natural log of the initial concentration of reactant minus K is rate constant and T is time. This reaction can also be written as, this is again natural log is to the base E. This is K rate constant 1 upon time T. This is again natural log initial concentration of reactant R naught. This is concentration after time T. When, since our log table R to the base 10, so we will convert natural log into log to the base 10 by multiplying it by 2.303. Then our equation becomes K is the rate constant is equal to 2.303 upon T log to the base 10. Remember that it is log to the base 10, it is natural log to the base E. This is again initial concentration of reactant and concentration of reactant after time T. According to this equation, B according to this reaction B, when we plot, this is natural log of the concentration of reactant against time, then this type of slope plot is obtained, and this plot has a slope is equal to minus k, and here this intercept will be natural log of initial concentration of reactant. In the same way, This was the equation which we derived for first order reaction. Here we can also write this reaction in this form. When we plot log to the base 10 of the initial concentration of reactant upon concentration of reactant on this axis and this time on this axis, then the slope is equal to k by 2.303. Similarly, we can also plot for this reaction which we derived earlier. This is natural log of the reactant, initial concentration of the reactant. This is natural log of the initial concentration of the reactant. This is natural log of the concentration of reactant after time t. And this is initial concentration of reactant. So when we will plot this natural log of the concentration of reactant after time t and against time t, then this type of plot is obtained, which is a straight line, and k will be equal to the negative slope. Here intercept is natural log of the initial concentration of reactant, because this equation is equivalent to y equal to mx plus c. We can also write this equation into log to the base 10. Here this is log to the base 10. So here this is log of the concentration of the reactant. This is log of the initial concentration of the reactant. This is time. This is rate constant. And when we will plot log to the base 10 of the concentration of reactant against time t, then the slope, this plot is a straight line, and here slope is minus k upon 2.303, and the intercept will be equal to log initial concentration of the reactant. So such type of plot can also be asked in the examination. For example, if natural log of the concentration of reactant is plotted against time, and the plot is a straight line with a slope of minus k and intercept natural log of the initial concentration of reactant, then what will be the order of the reaction? If order of the reaction is given, then the slope can be asked. In the same way, here we can ask the question, when log to the base 10 of the concentration of the reactant is plotted against time for a first order reaction, then what will be the slope or intercept for this plot? This is half-life period of a reaction. What is half-life period? During a reaction, the reactants are converted into product when the concentration of the reactant is reduced to half of its initial concentration. That time is known as half-life period of the reaction, and it is denoted by T half. It is T half. This is the symbol of half-life period of the reaction. And for a zero order reaction, we derive this relation K is equal to R naught was the initial concentration of the reactant minus R is the concentration of the reactant after time t. If we take T half in place of time, then this concentration of the reactant will be half of the initial concentration of the reactant. And when we put this value of R in this equation number 1, then we get this relation R naught minus half of R naught upon T half, or here for a zero order reaction, half-life period T half is directly proportional to the initial concentration of the reactant. But in case of first order reaction, the relation is different. Here this is the half-life period for a first order reaction. This relation we derived For a first order reaction where K is called the rate constant, T is the time, R naught is the initial concentration of the reactant and R is the concentration of the reactant after time T. So after T half, this concentration of the reactant R after time T will be equal to R naught upon 2, means it will be the half of the initial concentration of the reactant, and when we put T half in place of T, then this concentration of the reactant will be half of the initial concentration of the reactant, that is R naught upon 2. So when we put this value, the equation becomes K is equal to 2.303 upon T half log R naught upon R naught by 2. Similarly, this R naught will cancel and the relation comes T half is equal to 2.303 upon K log 2, and log 2 value is 0.3010. So when we multiply this value, we get this relation: half-life period for a first order reaction, it is not depending upon the initial concentration of the reactant. Means T half or half-life period for a first order reaction is independent of the initial concentration of the reactant. But in case of zero order, it was directly proportional. So when we plot T half concentration of the reactant for a zero order reaction, this type of plot will be obtained. Means half-life period is directly proportional to the initial concentration of the reactant. But in case of first order reaction, the T half is not depending, it is for zero order. But for first order, then we will see it is T half, it is R naught. When we increase or decrease R naught, T half is not changing. It means T half is not depending on the initial concentration of reaction for a first order reaction. So this is all about the integrated rate law method.